Oh my goodness.
I didn't taste the food.
The next labs we're going to work with is pressure sensors. Of course, we know the definition for a sensor, right? Everybody okay there? Okay. And of course, we talked about position sensors. We talked about speed, weight. Haven't talked about count. Haven't talked about flow, temperature, lightness, thickness, time. We talked about motion, proximity. We talked about well, what we haven't talked about is pressure. What is pressure? Force, gas. Can't really say it's a force because it takes pressure to create a force. So we can't say force, pressure is a force, right? Well, it's not going to be gas, it's a fluid. So we need to have fluid. And we need to have motion, right? You understand that? To create a pressure. Absolute pressure, y'all y'all understand those names, those terms, absolute pressure relative to perfect vacuum gauge pressure, relative to atmospheric pressure, which most of your pressure gauges measure. A vacuum pressure, and what's a vacuum? Now, it's pressure below atmospheric pressure, right? Measured low pressure relative to perfect vacuum. Differential pressure, we work with those every once in a while. This is the difference between two pressures. And SEAL measures pressure relative to a fixed pressure. Okay, so these are the terms that we'll run into when we start talking about sensors that sense pressure. So they're going to either sense absolute pressure, gauge pressure, they're going to sense vacuum, or different pressure, SEAL. Okay? Okay. This is supposed to be the number two, not the ratio. It's wrong. You go, where is that PowerPoint at? Yeah, I know it is. These are what we measure, units that we measure pressure in. Normally over here we use what? PSI or inches of mercury. Where do you run into inches of mercury at all the time? Well, the weather forecast, that's the way they give the atmospheric pressure, they give inches of mercury, right? Then we get into torr, which is just another way of representing this, right? Inches of water, inches of H2O, and then we have the Pascal, which is broken down into Newton bars, and kilograms per centimeter. I'll have to go back and look at the torr. I think it's pop in my mind. Okay. So when I look at a gauge, it's going to be in one of these, or a sensor is going to be in one of these units. Usually we understand PSI, right? And that means inches of mercury. We see that in the weather when they talk about inches of mercury, when they talk about low and high pressure. That's what they give it. Inches of H2O. And this would be more on ISO standards. And that's standardization column.
Now, inches of mercury and inches of water we use in inches. Well, honestly, I've never seen that. I never had it.
Inches of water?
Inches of water or inches of mercury.
Both of them are used in different applications. And an application, I'm going to give y'all what's the news guy? I have no application in my mind right now. But these are, when you look up pressure units or you research it, these are the ones that they give that it could be.
Okay, I was just curious if they're ever used in industry, that, I mean.
Yeah, over here, it's either the top one or the bottom one.
Right. I've seen a lot.
See this.
I probably see more bars than I see these.
Yeah, bars is just another way of representing pascals. Because pascals is such a big unit. So a bars is just thousands of pascals. So 2 part, well, actually, I think it's 10,000, right? It's big. So pascals is a very, very small unit. So it's just a way, kind of like we use engineering notation. So pressure is, this is this is the definition of the pressure. So so this is where we get into kind of a loop, right? You understand? So what is a force? So how would we define a force? Oh, there's something up there.
Something because of changing motion.
Or the shape of an object, and if you look at it, sometimes it's defined or tends to cause something to change in motion. Because sometimes we can apply a force and we can't move something, right? It's unmovable. So force, so pressure is equal to force divided by. Well, how do we create a force? What's required to create? So PSI. So that's one of the measures. That right there explains it exactly. What does PSI stand for? What does PSI stand for? Per square inch. Square inch. So normally we use square inches. We're designated an area, right? You understand? Yes or no? So what's A? Area. Yeah. So the amount of pressure that's required to generate this force. So force is equal to, if I redo that formula, and this is, you take pneumatics or fluid power, this is one of your main formulas. Force is equal to what? Pressure times area. So that's one of our main formulas in fluid power. Okay. So this is the same formula, it's just been transposed. Yeah, any 3-term equation, you can use the circle or the triangle, whichever way you prefer, right? And we come over here and do that. And then this is on to the side, so I'd put that right here, right? You understand that? And then I'd put that and that. So that means pressure, force would be equal to what? Pressure times area, or pressure would be the amount of force that the pressure generates divided by the area. So we can't have pressure without generating force. Does that make sense? So pressure is the resulting from a force of 1 or more pound force applied to an area of 1 square inch. And this is if you're using pounds per square inch. So this is one of your main formulas, and this is why the advantage of using high pressure. What's the advantage of using high pressure over low?
High pressure or low pressure, you can work with a smaller area.
Right, you can work with smaller actuators, right?
Yeah.
So the higher the pressure, so this is one big advantage hydraulics has over pneumatics.
Yeah, like
Is that we can have extremely high pressures, which means our actuators are going to be small, very small. The planes that I worked on in the Navy, the hydraulic pumps were 3,000 psi. And the actuators that move the control surfaces, and this is a big old plane. P-3 Orion is a big plane. Little old tiny one. But you think about it, with 1 square inch of area, 3,000 psi, you could generate 3,000 pounds of force. Well, that basically means you can move a 3,000 pound load minus the friction below. So this is PSI. Everybody okay there? We should be okay with PSI because this is the one that we run into most often. Even if you feel the air up in your tires, you understand pounds per square inch.
Pretty plain.
And ain't that neat though? You got, the P3?
Yeah.
Yeah, that's what I used to work on. They're phasing them out. That was my plan. So, yeah, it's a subject and destroy. Its primary mission was to seek and destroy submarines. That was its primary mission.
Put people in the sea.
Down the water, feeding sharks.
Now this is what inches of mercury. So the pressure exerted by a circular column of mercury of 1 inch in height at 32 degrees centigrade or water at 39 degrees centigrade at a standard acceleration of gravity, which is a big term. So basically you have over here you have a vacuum, right? You understand? Over here we have a pressure. So what is a vacuum? A vacuum does not necessarily mean the absence of a pressure. Everybody understand? What is a vacuum?
Negative.
It's a negative pressure, but we don't have to have what we call. So normally people, they say a perfect vacuum. So a perfect vacuum is something where we suck all the pressure out, right? You understand that? But we have a lot of vacuum. So when so we have a certain amount of mercury, we apply a vacuum and it's going to pull it and then measure the vacuum over here is the mercury. High pressure, and this would be positive mercury, and this would be without, this would be like at sea pressure. See those? Be okay there? And you'll learn about the only place right now, right off my mind, is running this is the way when they talk about high pressure, low pressure in the weather, they call what? Inches of mercury.
I've heard it.
Pascal, this is an ISO standard of pressure, so a lot of things are going here. So when you get into Mercedes down there, odds are all their pressure gauges are going to be in pascals or bars. And it was 10,000. So bars are just another way of generating pascals. So 1,000 kilopascal is equal to 1.45 psi. So I fill my tire up, the 32 pounds, that's going to be thousands of pascals, right? You understand? So that would be real hard for a meter to keep up with thousands of pascals. So they came out with a method called the bar, and the bar is equal to what? 2,000 pascals. So 3 bars would be 30,000 pascals. And then of course we could figure out how many psi that. Are we okay? So this is the ISO standard, or International Standard, SI standard, the way we mount pressure. Of course, this is the way you calculate pascals. The number of newtons divided by the minute. So we're still dealing. So in the metric system or in the International Standard System, they use newtons to represent force. And I don't know what that is. I have to look that up. And then, of course, it's the same formula, so pressure is equal to the force divided by the area. But the international standard of measurements is meters, right? So we use pounds per square. We use area. We use inches, square inches, right, or square feet, or something like that. That's the way we do over there. They do square meters. So the formula itself is exactly the same, right? Well, this is rounded, by the way, so that little fine, and this is not perfect. It's close enough of that. But it's really fine. It's just like pi. What do we use for pi in AC? Yeah, we use 3.14. How long is pi?
Forever.
We don't know.
We don't know.
We don't know.
Never seen the end of it.
Never seen the end of it. So, So,
Still
but that's
probably
accurate
higher.
enough, and that's what I tell people, you know, when they see, by the time you hit the pi key on your calculator and get that 13-digit number, you could already enter 3.14. You're a lot more accurate than you need to be, right? You know what I'm saying? So a lot of times you can get a rough estimate just by using 3. It's not gonna be, we like to be a little more accurate than that. Are we okay?
One of the instructors at US still had high memorized 30.
Yeah, there was some kid on one of that thing that Steve Harvey does. I forgot. There was a lot of digits. A lot of digits. It was just unbelievable. Last time I checked, they had calculated it to over 1 billion digits, and it still hadn't fell into a repeating pattern. I think I told you about the person of interest, Harold personally, about every number that's ever been written is somewhere in pi.
Yeah, but it'd be funny if
Yeah, your social security number's in there. It's just that you don't know where, right? There's a place on the internet, you can get pi, and it brings up 1 million digits. It just keeps going and going.
Why would you do that?
Yeah, you have people that just do stuff like that, you know, because they
I'm
want.
able with 3.14.
Yeah, I'm okay.
It's a pretty cool symbol.
I do
The
like
force needed to, so a Newton is the force needed to accelerate 1 kilogram of mass at a rate of 1 meter per second squared. So that would be the formula for Newton. Basically, in this class, you don't need, a Newton is just a method of measuring what? Force. Pascal is a measure of pressure. Of course, area is area, right? What?
Pi.
Oh, pi.
lemon or chocolate.
Lemon. Oh, this one's apple. Yeah, I will.
This is a pressure conversion card. These are available on the internet. I wish I'd have gave the person credit for this. I didn't have to do that. I've had to grab it stuff off of them there. Not credited. And a lot of stuff on the internet is credited. So this is just a chart. Y'all have this available up to you if you get into a situation where you're trying to learn a new pressure system or a new force system. Then these charts are available. You're more than welcome to go in. But this gets PSI, millibars, bars, atmospheric pressure, Pascal, kilopascal, megapascal, millimeters of when you get into the inches of mercury, right? I mean, not mercury, water. And then this right here would be mercury. And this right here would be, well, that's just a formula, kilograms over centimeters.
Now, we were talking about, I was talking, any common knowledge. You don't have to, very common knowledge.
These are different gauges, and so this one measures what? So here we go. There's a gauge right there that's what? Can y'all see that? There's inches of water right there. By the way,
But for every,
in my infancy in these things, we got one of these gauges, and it looked like it's full of carbon. What's wrong with the gauge? It's got goop all in it. Of course, y'all know what that is for. Or what is that? No, what's that in there for? It's a dampener, is what it is. Yeah. Dampener. So it keeps the needle from vibrating. So it's in there for a dampener.
What is that?
It's just a silicone based compound. So it's a goop is what it is. And that's what it's in there for it helps keep moisture out of the gauge for one thing, but the main purpose it's in there is to dampen the meter. So anytime like when you're running on a compressor or pressure gauges, you don't want the meter to just constantly vibrate, which over time would tear that meter up.
Do all of them have silicone?
No. Huh?
Do all of them contain silicone?
No, it's the only ones I've seen contain soap. I'm not saying that's not.
I'm just kind of curious.
I know they don't use water.
Because rose and silicone pretty clean.
But they do have gauges that's got stuff. Well, you might need to find out what it is because, could be an oil base too. All we want is something that's got a viscosity that doesn't change a lot with temperature, that you can see through. But it's got to be something that has a pretty, they don't freeze on you, right? And it don't change viscosity, it don't change thickness. Because if it changed thickness, then it would do what? It would, at real cold temperatures, it would impede the gauge too much. But that's the main purpose of that stuff in there is to keep that gauge from just sitting there doing. Yeah. So we called up the company and said, something busted in that gauge. It's supposed to be in there. Digital, this is, so blood pressure gauges, so blood pressure monitors, anybody got one of these?
Oh, yeah.
I got one too. This is a wristband. These things are not extremely accurate. I got one that does one. These measure in one. Yeah, but if you look at somewhere on here, yeah, so right here, you look on your gauge, it's actually. So yeah, you run into that all the time.
Oh, I know, I look at
Well, donuts don't mess up your blood pressure. Sensing element. Sensing element. So this is the basic makeup. We've already looked at this several times, right? Everybody okay on these components, the function of each one of them? Sometimes we have to condition the, sometimes we get the signal out here. Sometimes we have to condition it to match our system. I think that was on the last slide with temperature, right? I think we've looked at a couple of these. Then I'll show y'all these. Bourdon tubes. Everybody okay with those? Yes, no?
I don't think that.
Must be done fine.
Oh, yeah.
So this is the Bourdon tube.
Also has the blind channel.
No, that's not biocatalytic in there.
Oh, this is the
That's pressure.
like
That's
the
the pressure.
like the whistle or the birthday thing.
Yeah, the birthday thing is a Bourdon tube. The birthday whistle, that's exactly what that is. So what happens when you blow into that and generate a pressure, which means you generate a force, right? What does that birthday whistle do? Yeah. And then when you relieve the pressure, what does it do? Retracts, right? Okay. Don't understand that. Huh? If it works correctly. So the Bourdon tube that you're looking at is this tube right here. But we also have what we call a helical Bourdon tube, which works exactly the same way. This will fit, these usually fit inside a round tube, right? I understand they take up a lot of space. Then we have what we call a diaphragm. Did I show y'all one of those? This is a flat. This is a flat guy. I showed this to somebody. It's like your lung.
Oh, I don't know.
And of course, I need to put these on my camera, so. Oops. This is a pretty good size bourdon too, which makes it pretty easy to see, right? So here's the actual bourdon tube right there. Now, of course, I think this had a mercury switch that was mounted right here. But you literally can, if I wanted an analog output, I could use a potentiometer mounted on this somehow. Here's where the mercury switch is mounted. And of course, when we put pressure into it, it causes it to do what? Positive pressure would cause it to expand. And this is against the dead stop, by the way, but you could also use these to measure a vacuum. So, positive pressure causes it to try to straighten out. Negative pressure would cause it to bend back together. Right? You understand that? So we could put a digital sensing element on this. Normally, pressure sensors, we combine it with something else. That makes sense? So this right here means nothing unless I combine it with something else. So I could make this move a wiper on a dial that indicates pressure, or I could put something in here, and then I can set a place where it trips, right? You understand that? See where it shifts right here? And that would be a digital, or I could take a pot, some type of potentiometer, and convert it to an analog output. It depends on what type of pressure sensor I have, right? We got two types of sensors, basic categories. We have digital sensors and we have analog sensors, right? You understand that? This is the flat diaphragm right here. And of course the diaphragm is in there. But when pressure comes in through this outlet, it causes the diaphragm to do what? To move. And this is where we would attach our sensing element would be attached right out here. So I could attach a potentiometer out here, right? You understand that moves with that, a linear potentiometer, or I could attach a little limit switch that hits up against and makes a limit switch and get a digital output. Now these are mechanical, right? You understand that? The last one they looked at, this is called a bellows. And it's pretty obvious how this works. So normally they're made out of a metal. So what happens is when I put pressure on it, what's it going to do? Expand. If I put a vacuum on it, what's it going to do? It's going to contract. And then of course this comes in and mounts a permanent on one side surface that don't move. So when the bellows moves in and out, we can use that to indicate pressure.
What actually measures pressure?
Well, that's what we're talking about. Normally these sensors have to be combined with another element to get a voltage or current or whatever output.
So I'm saying, you use like an encoder?
Could use an encoder connected to the bellows. If I wanted a digital output, probably these guys would be less than 360 degrees, so it'd probably be an absolute encoder. I could use a potentiometer. So when it moves, I could use an LVDT. You know, anything that senses motion, we could use to output on this pressure, convert it into an analog signal. If I'm going to convert it into a digital signal, then I could just hook a limit switch. When it expands so much, it'll hit the switch and convert it over. We could make this part of solid state sensors usually use semiconductor sensors. Well, they actually work on the characteristics of a silicon that actually changes its opposition with pressure. Good. Yeah, all we're trying to do right now is just look at how do we sense it, right? How do we sense pressure? And these are just the way we sense pressure. We sense the pressure, but then odds are we're going to have to do what? We're going to have to combine it with something else. I don't see my PowerPoint over here. How in the world did I close that out? That's not it. Always amazing. Now, E works on basically the same, we don't have one of these, I think I might have a press picture. It works kind of like this, right? Understand? But the ridges are across the surface, and it's still gonna do what? Still gonna generate a motion. I think I do have some pictures in the next slide. So that's our sensing element, right? You understand that? And this slide point didn't talk about this. It does. The transducers. So we got piezometers. Everybody okay there? Piezo. What is the term piezo mean? So we got piezo resistive and piezo. Lots of pizza. Make that a pepperoni pizza. So basically what piezo means is that it's affected by pressure. So piezo resistive, slow down, Rich. Piezo resistive means that it changes its resistance with what? Pressure. Piezoelectric means it generates a voltage with what? With pressure. Anybody that smokes, in the old days we had cigarette lighters, and they're still pretty popular, that uses a flint. You spun the little thing and it generated a spark. Most people don't use those. I know they still make them, but they're pretty expensive and they're collector items too. It's hard to get the fuel for them now too. Used to, every store sell a lighter for it. Now they sell containers. Yeah. So, you guys get all right? Yeah. I got one. Piezoelectric is what you're doing when you got the newer ones where you have a little thumb thing, you hit it, it's that piezoelectric crystal, generates a voltage that's high enough to do what? Generate it all. You're seeing a perfect example of piezoelectric. A lot of your gas grills have a piezoelectric device in it. You press that button, you hear it pop, right? Yeah. When it pops, what it's doing is hitting that crystal, and it's piezoelectric. It means it generates a voltage that's proportional to a pressure. You're generating a lot of pressure real fast, and it generates a pretty good arc, right? Yeah. Yeah. Inductive to talk about. We used to take a car coil, and put it inside a cigar box. Ever did that? You put aluminum foil around it and isolate it. When they open it, breaks the circuit. I'll tell you about the nail in the chair at US Steel. Yeah. Had the gate opener where you could do it remote control. Inductive, the LVDTs, capacitive, and a little while piezoelectric on your slide. Everybody okay with Bourdon tubes? Right? Of course, this is basically what I got up here. Diaphragms, everybody okay there? Yes, no?
Yeah, where do you find them bellows at? Kind of overcooked you find bellows.
The bellows is used inside. Sometimes it uses it, but you don't know it uses it, right? You understand? The bellows is usually a little more accurate than the Bourdon tube because the Bourdon tube is pretty solid. These guys are more at lower pressures, not real high pressures. So Bourdon tubes are used a lot with high pressure lot for this guy right here. What does this guy measure?
Different.
Yeah, difference in pressure. So what we do is just mount it up here. This rod actually moves. We put one pressure into it, it's trying to push the bellows, compress the bellows. We put other pressure into the bellows, and it's trying to push it out. And what would you get? You would get the actual differential. So differential pressure is usually a lot.
What type of scale would you use for the engine you're trying to measure?
Yeah, well, any of those units that we looked at, TSI, it depends on where you're at, bars, or. This is the bellows used inside an actual, I don't know, this is the, so what they've got is they've got a lever right here. And whatever the sensing element is going to be the transducer. These are the capsule types, so yeah, I did get a picture. Pretty neat, right? What have I seen this? I've seen them too.
So powerful.
Now on the powerful, I've seen them in something.
No, I've seen them actually. I've held one.
These are what's used in most of our solid state pressure sensors, which is what we got. It's either going to use a piezo or resistive, or it's going to use a piezoelectric. Now the problem with piezoelectric is they only generate force when the pressure is originally applied. Now understand what I'm saying? Yes or no? A perfect example is your cigarette lighter. You come down and you pop it, that thing comes down and hits the piezoelectric crystal, and as long as you got your thumb on there, that pressure is still being applied to the crystal.
Oh.
It's not generating a voltage with pressure, it's the generating of force with the change of pressure, right? So piezoelectric works really well for a change of pressure, where you want to see a pressure change. But anytime the pressure is not changing, then a piezoelectric would not put out a voltage. When it is compressed or expanded, piezoelectric sensors change their what? Their resistance. So the only time we run into a piezoelectric would be if we're dealing with something that we want to measure a change in pressure. Piezoelectric, of course, crystals produce a difference in potential when compressed or expanded. So what does it require? Okay. Motion requires motion. Not used in static pressure systems. Used to measure turbulence, blast, ballistic, or engine combustion. These would be really good examples. Okay. And this is just a picture of a piezoelectric solid state sensor. Huh? It does. So what they got is sensing the pressures down here. Pressure comes in half of the right one. Pressure comes in the top. It's going to cause this to compress the piezoelectric plate right here. It's going to produce this guy produces a voltage that's proportional to pressure. But the problem is it requires what? No, we don't have to fire these things up. No. But they don't measure static pressure, they measure what? Change in pressure. Everybody understand that? So you gotta have a change of pressure because you gotta have motion. So piezoelectric requires that second thing, requires what? Motion. So right now, this is a piezoelectric crystal that's generating the motion, but what's happening constantly? It's in motion. If it was to come up here and stop, then the voltage will drop down to what? Zero.
That's exactly what a spark plug is.
Well, a spark plug don't generate a voltage. You got to feed it with your car battery.
Yeah.
A piezoelectric generates a voltage. So this is coming James, this is coming from the crystal. This is not coming from your battery or your power system on your car. So piezo resistive is basically very similar to load cell. Similar to the strain gauges, silicon changes its resistance when what? Pressure. Except load cell uses wires, where piezo resistive uses silicon. But it works on exactly the same principle. So if we mount these things and notice that they're in, we mount them inside a Wheatstone rig. And these guys right here, these are just about all of your solid state pressure sensors used. These guys right here. So the one that we got is a pretty neat, but most of the lab, so how do we set the temperature sensor? Yeah, we set the temperature sensor with knobs. Somebody go get one of the pressure sensors back here. And as soon as James brings it back up here. So on this one, the bottom one, they call the top one. I'm sorry, they call set, and the bottom one they call reset. So set is where you're going to set the high pressure, and then reset is where you set your low pressure. Right? Understand? Huh? Yeah, I'm sorry. Yeah, temperature on this. Got pressure on my mind. It's the one that's got the digital readout on it. So this looks like it's so brown, black, blue, white. So this is a 4-wire sensor, right? So it has a normally open, normally closed. It runs off of DC, so we have an interface built in on the board. One of these are going to be, when power's on, that's when it's going to, the biggest portion of this lab is what? Figuring out how to program this thing. Well, so what are you going to do? First of all, you probably have to set, this one is set up to sense. Can you see what this is set up to sense? PSI. So that's one thing you have to remember is that when you get these things, you're going to have to specify what units the thing is going to actually measure. This guy here can measure vacuum or pressure, either one. This, by the way, this is what's nice about pneumatics. Pneumatics run at such low pressures that instead of using metal tubing or reinforced piping, we can actually use plastic. These are quick disconnects right here. Huh? Yeah. These are little quick disconnects. So to get it out, you have to pull this down, and then that releases it. It's got some fingers in there that you actually come in there and grab it. And then when you push it in there, normally we push them in, but literally when the pressure comes into the system, it'll come up there and seal it in, which is pretty neat. So in we should do what? Latch it. Yeah, I'm sorry. Yeah, I got that, bro. Thank you. So when you put pressure on it, you'll notice this thing, it'll try to pull the tube out and it automatically seat itself. But when you get it in, it's real hard if it's under pressure, by the way, to push that thing in. But that's the way we would take the tubing out. We'll probably have to do this probably in groups of 3s. We'll have to do them in groups of 2s. I think we'll figure out how to work that out because we just don't have enough. It's not that we don't have enough of these. It's that right now the little compressor we've got, it's only set up to handle 2 stations. And we had to do some rigging. We had to do some rigging on that. I just bring it up to you.
Make it that far?
What's that? We should. Some of y'all are fixing to start working on the third thing, and we might try to do maybe just one section of it instead of trying to do all three labs. We may just next class just break up and do one. Let the whole group. We might just instead of doing two groups, we might do it as a whole group, just to give us a tendency to look at this thing. And of course, this is a lot of your pressure sensors are not this complicated, right? But more and more sensors are going to where you program them with a digital readout instead of doing it with a dial. Of course, I don't know why, because these guys right here are just so, to me, it's so straightforward. These guys right here, you got to figure out or get a manual on how to operate this thing and move through the menus. So these things have menus where you don't have to do what? You have to go to the menu and set certain options. But these guys here give you more capabilities of the sensor. So we can probably do this. And the main part of the lab is teaching you basically how to program the sensor. Gets you used to using data sheets and stuff like that where y'all would do that. So guys, that's it for pressure sensors. Y'all got any questions? Yes, no? So pressure sensors are going to be on the test Tuesday, right?
Are you gonna make the review available?
Yeah, it's ready right now. All I got to do is just make it available. It's ready right now. I didn't say it's available right now. It's ready. Huh?
No, is it?
Yeah, y'all go ahead and take a break. We'll come back and we'll be in lab. Somebody turn on all the lights for us.